So in previous sessions, we've discussed derivatives and concepts related to them, such as finding local extrema and optimizing, right? Given a constraint, finding the extrema along a curve. Well, we're going to shift gears here from talking about derivatives and their uses to now integrals. And we'll start by talking about double integrals over rectangular regions. Okay? Now, from functions of one variable, the integral here was discussed as being the area under the curve. Okay? So you had the area under the curve from x equals a to x equals b, and that was how we thought about the integral of a function of one variable. So how should we think about the double integral of a function of two variables? Well, it will be the volume under the graph. Okay, so above a certain region, R, the double integral will give you the volume under the graph and over that region. So how can we formally define this process of taking the volume under the graph? Well, we've done Riemann sums for getting the area under the curve. We're going to do something similar here. You could see our region, x is between a and b, and y is between c and d. You could vary these. For example, here we could make d greater and less, and on and on. Well, how do we approximate that volume? We could approximate it by then taking each rectangle and finding the value of a function above that rectangle. Then that will give us a height of the rectangular prism, and so we take the area of the rectangular prism, multiply it by the height given from some value of the function, and we will get the volume of the rectangular prism. We could do these for each of these rectangles, but as you can see, that's not going to give us a really good approximation. So what we could do is then increase the number of divisions. Okay, so if we increase the number of divisions, then summing up all the volume of the rectangular prisms will give a better and better approximation of the volume under the graph. So here you could see the rectangular prisms all together, and you could also see that as we increase the divisions so that the area of each of the rectangles gets smaller and smaller, we get better and better approximations for the volume under the graph once we sum the volume of all of the rectangular prisms that we've obtained through getting a partition of our rectangular region. So then we'll formally define the double integral as the limit as delta goes to 0. So as these rectangles in our partition get smaller and smaller and smaller down to the limit of 0. And this here, this is the height of a rectangular prism. This is the area of a rectangular prism. So both of these should give you the volume of a rectangular prism. And we're summing all of the volumes of the rectangular prisms. And so the double integral is formally defined as the limit as delta goes to 0 of this process.